I'm Mr. McBrien. This is SCH4U, bond energies, and enthalpy. The Ontario curriculum would like for us to be able to compare the energy change from a reaction when we think about the bonds that are formed versus the ones that are broken. And we need to be able to explain these changes in terms of, well, endothermic and exothermic reactions. And this is what we're going to do today. So let's take a few steps backwards and let's talk about what bonding is. We know that bonds are the sharing of electrons. And we know that bonding is energetically favored. What do we mean by that? It means that the molecule that's formed when we pull fragments together or atoms together is more stable than its parts. In other words, if we pull together the pieces of a molecule, we'll get some energy in return. So if we think of our classic Lewis diagram then, on the left-hand side we have a hydrogen atom, another hydrogen atom, and an oxygen atom. And these are isolated in space. They're not bonded together. In fact, those are very high energy. It's a very high energy situation. In contrast, if we allow the hydrogen to form a bond with the oxygen, sharing an electron, and the other hydrogen to form a bond and to form a water molecule, well, this is a lower energy situation. In other words, if we pull those things together, we get energy. Now, we've already looked at that in terms of delta H, but we can also look at this in terms of, on the left-hand side, we have no bonds. On the right-hand side, we formed two hydrogen-oxygen bonds and gotten energy in return. Well, we can take the logical step of assigning half of that energy that we get back to each one of those bonds. In other words, the bonds have an energy associated with them. And when we do this, we're going to find that it's a very valuable exercise. So the idea that we're talking about here is bond energy or bond dissociation energy. And that's the energy that would be released if we formed a bond, or the energy that would be absorbed, that would be needed if we want to break a bond, if we want to pull those things apart. So that's what the bond energy is. Now what's kind of neat is it's fairly constant across molecules. So the carbon-hydrogen bond in methane has a bond energy of 413 kilojoules per mole. Well, as it turns out, the carbon-hydrogen bonds in ethane have a very similar bond energy. So here are some examples of bond energies that have been characterized fairly well for us. So we have hydrogen-hydrogen bonds, i.e. in a hydrogen molecule, are about 432 kilojoules per mole. Now if we contrast that with a carbon-hydrogen bond, well, guess what? There isn't much difference. Remember, both of those are sigma bonds, and the electronegativity of carbon versus hydrogen are similar. So no great shock that they have similar bond energies. Carbon slightly different at 347. Carbon-oxygen, 358. So these single bonds all have a fairly consistent energy with them. In contrast, we have an oxygen-oxygen double bond here, which has a much higher bond energy. All of these numbers quoted here are averages, and when we consider component bonds within precise molecules rather than generalities, there will be some deviations, and we'll actually talk about some of those deviations in a few minutes. Okay, so in a reaction, we can actually look at the sum of all of the energy that's absorbed from breaking the bonds of the reactants. And we can look at all of the energy that is released in making bonds for the products. And if the energy released is greater than the energy required, well, the reaction is said to be exothermic. And this, by the way, is just a facet of the first law of thermodynamics again. Energy can't be created or destroyed. So one way of looking at this, energy of the bonds broken, less than energy released from the bonds formed, well, that's an exothermic reaction. And here's a picture of one, and we're going to revisit this picture several times over the coming days. But for now, I just want you to focus on the potential energy versus, well, completion of the reaction. So on the left-hand side, the reaction hasn't started. On the right-hand side, it's completed. So it's all reactants on the left-hand side, all products on the right-hand side. And it's a good idea if you get comfortable with this picture because we're going to talk about it multiple times over the coming days. Now, let's take the combustion of methane as an example. So methane reacts with 2 oxygen molecules to become oxidized into 1 molecule of carbon dioxide and 2 water molecules. Now, what we can do is we can look at the energy levels of the reactants versus products and say, okay, this is an exothermic reaction because they have less potential energy when they're finished. Energy is given off. But now we can talk about it in terms of the bonds involved as well. So on this side, the reactants have energy associated with 4 carbon-hydrogen bonds and 2 oxygen-oxygen bonds. And on this side, 2 carbon-oxygen bonds and 4 hydrogen-oxygen bonds. And so what we can say is there's more energy released when we form these bonds than we have to put in to break these. For now, I'd like for you to ignore this part of the diagram and think instead of just the energy here versus the energy here. Now, the difference between those bonds, no great shock, is going to be this change in potential energy. And we can measure this. The enthalpy change is negative 824 kilojoules. That's what we would get if we were to combust that and measure the energy that comes off. Now, the corollary is true. If the energy that is absorbed from breaking the bonds, from broken bonds, is, in other words, the energy that has to be put in to break the bonds is greater than the energy released when we make the bonds, then the reaction is endothermic. And we've got a good picture here. It's kind of the mirror image of what we just saw. Our reactants, let's start from the point of view of our reactants, carbon dioxide and water. Theoretically, we could regenerate methane and oxygen from these. But if we wanted to, we would have to put energy in. So we'd have to break all of these bonds to form these. It does not matter if we actually go through that kind of mechanism. Remember in organic, we touched on the idea of are the bonds actually just breaking like that? In fact, they almost never do break precisely in that form. It doesn't matter because of the first law of thermodynamics, the law of conservation of energy. We know that the difference between the two states is all that truly matters. Okay, and again, the first law implies that if we do this exercise, if we can find a way to do the reaction to turn carbon dioxide and water into methane and oxygen, we will have to put in this amount of energy. So we could measure those things if we're lucky. In one case, it'd be easy to measure, in the other, a little more complicated. But in fact, now that we have this new trick of bond energy, we can estimate the result if we were to do that, even if we can't find a mechanism to do the reaction, especially directly. So what we can do is we can say that the enthalpy change will be the sum of the energy we have to put in to break the bonds minus the sum of the energy that will be evolved when the bonds are formed. So if we take our example of combusting methane to form carbon dioxide and water, we now know that we can sum up the energy from the bonds broken. We have 4 carbon-hydrogen bonds and 2 oxygen double bonds. And we can go and look these up on our handy table and sum them all, and we can see that the energy that would be required to take a molecule of methane and 2 molecules of oxygen and turn them into their component atoms. So the sum of all those energies would be 2,642 kilojoules for each mole. So that's the energy we would need to put in. We can figure out the energy that we would get out by seeing what happens when we form the bonds. So the sum of the energy from the bonds formed is 2 carbon-oxygen double bonds plus 4 hydrogen-oxygen bonds. We look them up in the table, and we get 3,466 kilojoules per mole. So when we form, if we were to take all those atoms individually and allow them to bond together, we would get 3,500 kilojoules per mole. And because of the first law of thermodynamics, then we can just subtract those things and get negative 824 kilojoules per mole. So that's how much energy would be evolved if we did that reaction. And this is the cool thing. If we wanted to do that other reaction that we'd have to work very hard to find a mechanism for, if we wanted to go backwards, well, previously we would have had no way to figure out how much energy we'd have to put in. Now we know exactly how much energy we'd have to put in. We simply reverse this equation and we get the result. Okay, so all of this is just an aspect of the first law of thermodynamics. But there is one approximation that's been made here. And I'd like for us to spend a few seconds thinking about this approximation actually, because it's a fairly interesting idea. So you might ask yourself, well, is every carbon-carbon bond the same as every other one? And we'd say absolutely not. Remember, we have double and triple bonds from our organic section. But even if they're sigma bonds, even if they're single bonds, are they all the same? Well, we can say that every molecule has a little deviation from theory on this. But we can find a really good example in organic chemistry to illustrate this idea. So, when we talked about ring structures in organic chemistry, we mentioned that there were lots of different ring structures right from cyclopropane up past cyclooctane. But the most common ones were cyclohexane and cyclopentane. So the question is, well, why? And the answer comes into this idea of ring strain. So remember, the perfect angle is almost exactly 109.5 degrees for tetrahedral angle. Well, maybe you remember that in an equilateral triangle, the angle is about 60 degrees. About 60 degrees. How about exactly 60 degrees? So let's change gears a little and let's actually go back to organic chemistry class. And let's look at cyclopropane. Okay, so cyclopropane, if we move it into 3 dimensions, you'll realize that you have no choice. If you want to arrange 3 carbons at equidistance, you're going to have a 60-degree angle. And that's nowhere near 109.5 degrees. And for this reason, it puts a strain on the bonds between the carbons in cyclopropane. Now let's try cyclohexane. So let's optimize this in 3 dimensions and have a look. Now you might be able to, from geometry class, you might be able to remember that the angle inside A hexagon is not 109.5 degrees. What happens is the carbon, the ring itself deforms into 3 dimensions in order to make something extremely close to 109.5 degrees. The ring strain, the strain on those bonds is almost zero. And similarly, cyclopentane also deforms itself in 3 dimensions to get very close to 109.5 degrees. So what does all this mean? Well, what it means is that in cyclopropane, we have bonds that are not as strong as the bonds in cyclohexane. This deviation from 109.5 degrees makes it easier to break the bonds in cyclopropane. Or, when the bonds form, it provides less energy back to us. What's the net result of this? Cyclopropane is more reactive, and it's also explosive because it provides lots of more energy than you would expect from a simple hydrocarbon. And we can quantify that ring strain by looking at the measured difference in bond energy, bond dissociation energy, bond energy, is very different from the 347 kilojoules per mole we would expect from a carbon-carbon bond. In fact, the cyclopropane bonds yield 115 kilojoules per mole less. So almost 1/3 of the strength of the bond is gone on the basis of ring strain. Okay, so to summarize our concepts here, the first law of thermodynamics implies that enthalpy changes can be calculated on the basis of bonds broken and bonds formed. The energy released when a bond is formed is fairly constant from one molecule to the next, assuming it's the same bond type and there isn't something special about that compound, like there is with cyclopropane. Most bond types have been characterized to some degree, so we can look those up in references for use in enthalpy calculations. We can use these to calculate the expected energetics of a reaction, even if we can't measure it with calorimetry. We can calculate the reaction enthalpy change by summing the energy required to break the bonds in the reactants and summing the bonds that of the products to determine the energy that should be released when they form. Okay, so please go ahead and do the bond energy calculation worksheet, and don't forget to review the notes page. Thanks very much. Have a great night.